bake sale or just a cigar? You should adjust it. You're coming for the team. Oh wait, you're varsity from there. What? You're not wearing these?
Gosh,
Your reaction makes it all worth it.
yeah, I'm sure it does.
Do you know what anybody needs direction?
As you can sense, all the jealousy that's just sticking out of it.
Y'all doing it over here.
I got yours, but
Alright, Joe, I see how this is. I'm just swinging on cold with it.
so bad.
It's not mine.
Yeah, it came over your bag. It's all yours. So this. But it has next year. Oh, is it also yours? And yours is this.
What? Is that your red square? Is that your red square?
Yeah. Oh, it does. We're playing Air Force Base.
Okay, we're down to the home stretch here, guys. So a lot of stuff to get through today. We're gonna wrap up our talk about pipe flow. By last lecture, we talked about laminar pipe flow, fully developed laminar flow through pipe. Today we're gonna get into turbulence. This is going to extend a little bit into the next and last chapter, chapter 9, and then we're going to be covering a lot of the basics of turbulent boundary layers today, so that'll speed up some of the last few lectures. Towards the end of class, I'm going to hand back your exams. I'm going to go over them briefly, but if you look up on Canvas, what I've done is instead of throwing in a kind of arbitrary curve on the exam, I looked at what that did, and in the end it didn't make a huge difference. The exam grades were overall much higher. The average was around an 85 instead of a 66 or something. So instead of just throwing an overall curve in, that doesn't help anyone a whole lot. What I'm doing is giving you an opportunity to pick 2 problems that you didn't do well on, resubmit those, and you'll get something like 30% of the missed points back for free. It's an optional assignment, so it counts as extra credit if you want. But it's a chance for some people that didn't do well on 1 or 2 problems to make up some lost ground on the midterm. And finally, I didn't think we were going to be able to get to it this semester, but the guys at the MHL moved heaven and earth, and we are scheduled to do a lab on Monday. It's scheduled during class time, okay? But I want to get a sense. Monday, you guys have something at noon. Is that right?
Yeah.
Okay. It would be best if we can squeeze it into to stay within class time, but for the sake of making sure everyone is able to do it comfortably, it'd be better if we could try to budget out 2 hours. Kind of show of hands if you object to starting it at 9 o'clock instead of 9:30. It's going to involve 2 groups. Could we?
I still practice, but.
Your practice. All right.
I can.
Well, so it's going to be done in two groups, one from 9 to 10, one from 10 to 11, if we're able to do this. And so if there are people with, I guess I should say that it's less than half of you objected to, or aren't able to make it tonight. What I'll try to do then is, Andrew, I'll make sure you're in the second group. So if there's anyone else with a time conflict that means they can't make it at 9 o'clock, let me know. But it's going to be at the MHL. Central campus, and it should be fun. It's a jet pump lab involving a pretty big model with a water jet installed in it, and there is not going to be a lab report. There's just a short pre-lab, which basically means using the control volume analysis we did in chapter 5 to predict the thrust produced by non-deforming stationary control volume. So standard, easy. Just want to, we're going to use it as a sort of, your predictions as sort of a meter stick for how well control volume analysis aligns with reality. But it's going to be, if you haven't been on the towing tank carriage, it's going to be your first time to get on there, turn some knobs, take some data, and it should be cool. All right, let's try to get through chapter 8. So in the last lecture, as I said, we talked about laminar flow through pipes. In particular, we addressed turbulence, sort of talked about what turbulence is, but today we're going to get into the nitty-gritty a bit more. So turbulent flow in general is it's a tough problem. There's no great way to describe turbulence exactly. And we don't really understand what makes it happen. In fact, all of this sort of random motion that happens with turbulent flow, we don't have the mathematical horsepower to track every single fluid particle and predict how it's going to move. And we don't really have the refined theories, things like chaos theory and fractal geometry, that give us a cleaner way of talking about this sort of randomness. There are developing mathematical theories that are better suited to describing randomness, as I said, things like chaos theory, but we're still not quite there yet. So in general, remember that we judge the character of a flow through a pipe based on the Reynolds number, defined as the speed times the diameter of the pipe over the kinematic viscosity. Below Reynolds numbers of about 2,000, called a flow laminar. So, for example, this is accelerating flow through a pipe. You know, you're increasing the flow rate gradually. It'll begin laminar. As you pass a Reynolds number of 2,000, you'll start to get these little turbulent bursts, meaning that this is where the flow is beginning to transition between laminar and turbulent flow. And then above a Reynolds number of about 4,000, we would call this completely turbulent. And so, this video shows exactly what's going on in this graph. As time goes by, the speed is increasing and you start to see these little waves developing, these instabilities, which get larger and larger and larger and eventually turn into what are called Kelvin-Helmholtz instabilities, and eventually become this really random sort of fluttering motion of the dye streak that's injected at the upstream end of the tube. So, we don't have a precise way of defining turbulent flows, but there are a number of characteristics which we see in almost all turbulent flows. And so it's one of those things where we can't really define it, so let's describe it. These characteristics are listed here. This guy from Texas A&M put together this list. I thought it was very eloquent. So first, we see that turbulent flows are almost always irregular. They're random, they're chaotic, they're fluctuating, and for that reason, we have to use statistical methods to describe them or to characterize them. Turbulent flows are diffusive. That is, there's all this crazy motion of fluid packets, and it causes an enhanced mixing of fluid layers. Unlike laminar flow, where you get flow with these nice clean sheets or layers past one another, there's all these random velocities that cause, on a macroscopic scale, that cause fluid particles to jump around between locations and carry with them intensive properties like temperature or specific temperature, kinetic energy, momentum, etc. And so anything you put into a flow, whether it's an increased region of temperature or it's an increased region of momentum, it's going to get spread out more quickly by turbulence. Third point here is that turbulent flows have large Reynolds numbers. This is kind of, it's a chicken or an egg sort of thing, but it's universally true that flow at very high Reynolds numbers becomes turbulent because laminar flows become unstable at very high speeds. We're not going to get really into this mathematically, but there's this idea that as you saw in the little pipe flow video, if you trying to remember how we close. If we have, for example, flow over a flat plate, we're looking down at the plate. What you generally see is you'll have these laminar flows. So if we have something like little dye streaks injected, well, this nice, clean, laminar progression of the flow, and then we'll start to get these little wiggles that develop into what are called Tolman-Schlichting waves that grow and become less and less stable, and it's sort of that these small perturbations grow with time. This is a characteristic of an unstable system. And so turbulent flows follow from the instability of laminar flows. Fourth characteristic is three-dimensional vorticity. You'll see in a video I have coming up here in a minute that one of the reasons all these velocities and such are fluctuating all over the place is that fluid particles are rotating in all directions. Right? It's if there's one word that you could use to describe turbulent flow, it could be swirly, and that happens with rotation about all axes. And so we have this these fluctuations happening along the U, Y, the U, V, and W velocity components. They're dissipative because there's all this enhanced mixing and all this fluid motion. Turbulent flows deposit a lot of energy. They perform a lot of work through the deformation of fluid elements, and all that work comes at the expense of the kinetic energy of the flow. And so you have this sort of cascade process where the pressure drives the flow, pushes the flow forward, causing a transition from potential to kinetic energy, and then the flow begins these sort of rolling motions and vortices, which pulls some of that kinetic energy out of the forward direction and dumps it into rotational kinetic energy. That cascades into smaller vortices and then these random fluctuations, which are eventually dissipated into thermal energy by viscosity. So as a result, turbulent flows require constant input of energy in order to remain turbulent. And these last two are sort of sanity checks on us more than the flows themselves. We have to remember that turbulent flows are still, they're still a continuum, meaning nothing has changed about the physical system we're looking at. All of the conservation laws still apply, and the governing equations are still intact, meaning Navier-Stokes are still accurate. It's just a lot harder to apply Navier-Stokes because now all of our velocity components, we can't sort of look at big chunks of fluid because there's so much small-scale random motion. And then finally, we have to remember that turbulence is a type of flow which remains distinct from the fluid that is flowing that way. In other words, we got to keep clear in our head that nothing about the fluid properties change when the flow becomes turbulent. There's different characteristics of laminar and turbulent flow, but in both cases, for our purposes, we have water as the underlying fluid. And so just keep the two separated as well as you can, the type of flow versus the fluid that's experiencing it. So I found this video. It's actually from the conference I was at last week, and it's there's this thing called the Gallery of Fluid Motion, which is like sort of artistic presentations of fluid motions. And this is a particularly nice video of turbulent boundary layers on the plate. I'm going to turn off the light so we can see it. They have this towing tank and this transparent window, right? With, I talked before about this thing called particle image velocimetry, involving these rapid little flashes of laser illumination with cameras taking short time exposed photographs that the computer then uses this statistical description to draw velocity vectors, right, and determine what the flow looks like. And so what we're looking at here are contours of, I believe, velocity. So we have the free stream velocity, and then we have this high velocity near the plate, which is getting dragged past the camera, right, indicating that we have the no-slip condition, right? The velocity of the fluid at the interface with the plate is the same as the velocity of the plate itself. We'll skip this little one here. All right. There we go. So when we talked about the diffusive nature of turbulent flows, you can see this is a really good illustration of what that means. If dye is injected right here, right? They injected this fluorescent dye compound. We can see that because of these random motions and these fluctuations toward and away from the plate, we're getting dye mixed way, way out beyond the edge of the plate. Unlike laminar flow, where we saw before, if you inject a dye streak into a laminar flow through a pipe or something, it just remains as a line. We can see here another example of, this is actually sort of a hybrid composite computer image, where again, plate moving past, and then they've used a algorithmic computer program to determine how a hypothetical distribution of particles gets dragged into and out of the boundary flow past the plate. So we can see all of this enhanced mixing, this really high, these large-scale turbulent or vortical structures, and this general swirliness of the flow. And hopefully you can gain an appreciation for the fact that, if nothing else, it's really messy. You know, we don't have a nice, clean way of describing it. Which brings us to one of the only ways we do actually have of describing turbulent flows, which is the so-called Reynolds decomposition. So Reynolds decomposition suggests that it's fairly intuitive. If we have this this fluctuating process, right? This fluctuating velocity, for example, on a pipe flow. Go ahead and draw a pipe. Flow through a pipe with some velocity u. The idea is if the flow is turbulent, then we're going to have this underlying velocity of u. But around that velocity, we're going to have all of these turbulent fluctuations. And so the Reynolds decomposition just says, all right, let's treat the instantaneous velocity as a sum of an average velocity, u bar, plus a fluctuating term around that average. It's not really shown here very well, but I want to make it maybe a little more clear. Yeah. Let's suppose that what we have actually is some time varying flow through a pipe. Let's say where the flow is decelerating, so it's getting slower with time. But it's also turbulent this entire time, so we have these high frequency fluctuations around this this sort of background flow. So this would be the average flow rate, this would be the instantaneous flow rate, and then what we say is that the instantaneous flow rate is just the sum of some, what we're going to call a slowly varying mean plus fluctuating component. So this U bar would be the blue line in the background. And then the total component would be this red line. So we could say that the fluctuating component then is equal to U minus U bar, which if we drew it would simply, look like something that's oscillating about 0. So this is a fairly intuitive process. It's just the idea of saying, we have an average and we have a fluctuating part. We can separate the two. The key is that we want to this average, this U bar here, we're going to define as U bar of t is equal to it's already written up there, T naught plus T 1 over T. The trick is recognizing that this T, the period of integration, is something we have to choose. And so the idea is we want to make it large enough that we average out all of the fluctuations about the mean, but small enough that let's say we want to pick T such that T is much larger than the period of the fluctuations, and T is much larger than that, and T is much smaller than sort of the time scale of the background unsteadiness in the flow. That is we don't want to lose, we don't want to average out all the detail of how the flow is decelerating, but we do want to average out all the turbulent fluctuations. So there's this kind of subjective step of picking a good time scale. If the flow is steady, if we're not worrying about the slowly varying component in the background, then our choice of T is pretty arbitrary. As is shown here, you can pick here to here, as long as it's large enough that you get some average, which doesn't really change with time. So, all right, what's the reasonable question might be sort of what's the use of doing this? It's kind of just a fairly, what might seem a fairly obvious way of breaking down the turbulent flow into these two components. But we're gonna write some more kind of obvious stuff here and then use that to develop some less obvious stuff. So, said before, we'll go and say U T is equal to 1 over T, T naught plus T, T. And so from these facts, it should be pretty clear that if we use the over bar here to define an average, that is, if we say that x bar is equal to T naught plus T 1 over T x dt. That is, if the over bar just indicates a time average over some period T, then U bar bar is equal to just u bar, right? It's equal to itself. The average of a number is itself. So the average of the average is its own average. U prime bar is equal to, say, 1 over t naught plus t, u minus u bar, dt, which is just equal to u bar minus u bar, which is equal to 0. Right? In other words, the fluctuating component is equally distributed about the average. This should be pretty obvious as well. Alright, so again, this is kind of you might ask, like, what's the point in all this? But the next thing we want to look at is not, just taking the average of the fluctuating component, but taking the average of its square. So if we take this fluctuating component, we square it, then what we go from is, if this gray portion is the fluctuating component only, the u prime, squaring it would give us this dashed line, which is always positive. And since it's always positive, it's integrating over this, taking this average then, has to be greater than 0. So if we define u prime squared bar, this is what we call the variance of the velocity. Okay? And it can be written as being equal to u squared bar minus u bar squared. So since this is this kind of describes the I guess the amount of total fluctuation that's occurring, right? The general fluctuating strength of the flow. And then if we go ahead and we take the square root of this, so we take the square root of u prime bar, u prime squared bar is equal to square root of u squared bar minus u bar squared, which is equal to, which we call the standard deviation of u. This could be interpreted as sort of the average, the mean different, or the average offset from the mean. That is the average deviation from our mean background flow, u bar. So this is, it's kind of all, none of it's hard, it's just a matter of keeping your bars and primes straight. But what this allows us to do then is, since we've decomposed the velocity u into these two components, and we've said, alright, u bars is not that interesting, it's its own average, it's just a number that describes kind of how fast the gross flow is moving. And then we're able to characterize the fluctuating component by a variance and a standard deviation. This allows us to write what we call the turbulent intensity. Or turbulence intensity is equal to, did I do the square root? Yeah, I did. All right. So this basically tells us the average deviation from the mean relative to the mean itself, which can be thought of as sort of a it's a kind of a proportional or percentage deviation, and it's a good way of describing overall kind of the strength of the unsteadiness in the flow. It's how gusty the flow is. For example, if you have two flows, or flow through two pipes. One flow, and in one case, your velocity, I don't know why I drew pipes, that was stupid. We don't need to actually draw pipes. Time u time. Alright, so if we have two different flows that both have the same let's say they're both 5 meters per second, sort of as the average flow velocity. But then we have this fluctuating component. I should bring it back. Which in this case is really large. We may find that the standard deviation of u is equal to maybe 1 meter per second, right? And in this case, let's say we have much smaller fluctuations. And in this case, we may find that standard deviation of u is equal to only 0.1 meters per second. So the turbulence intensity of these two cases, in this one we would have I is equal to 1 meter per second over 5 meters per second, which is equal to 0.2. And in this case, we would have I is equal to 0.1 meters per second over 5 meters per second is equal to 0.02. So, in other words, we would say that this flow has a 20% turbulence intensity, this one has a 2% turbulence intensity. And so just from looking at these two numbers, it doesn't matter what the background flow velocity is itself. We're able to sort of see how proportionally unstable and fluctuating it is. So in general, we would just be able to look at these two numbers and say this is a much cleaner flow and less turbulent than this one. Point of note, this is a big thing that you'll see to characterize like water tunnels or airflow or air tunnels that they use to test ships, propellers, airplanes. Usually in the specifications, they'll have something that characterizes their inlet turbulence intensity. That is the amount of fluctuation that's coming in and hitting whatever model you're testing. In a towing tank, it's a lot harder to do because the water sits more or less still, right? So you're dragging something through quiescent fluid, so this will generally decrease to 0 with time. You drag a model through it, it stirs all the water up, you get this turbulent motion. You may have, you'll have some turbulent fluctuations and 0 mean velocity, and so your turbulence intensity shoots way up towards infinity and then drops back down towards 0. But in a flow channel, you usually see turbulence intensities in the order of 1 to 5% in recirculating water and wind tunnels. Okay. So, you hopefully remember that for laminar flows, we had this nice handy relationship between the strain rate and the shear stress. Right? Namely that the shear stress is equal to the viscosity times the strain rate. And this was nice. It may seem like a reasonable approximation to sort of in the time average to apply the same relationship to whatever the background velocity of the turbulent flow is. Right? But this is actually not correct. You can't look at the U-bar term here in the same way that you do the U-term. In other words, all of these random fluctuations, you can't just average out and then use the background flow to compute the stresses. This has been tried, it's been shown that it's incorrect, and the reason that it's incorrect is because the mechanism of shear stress for these two cases is very different. So we can kind of look at this as a, say, if I draw one of these velocity profiles. Oops. We'll say we won't assume whether or not this is, or whether this is turbulent or laminar just yet. But what I want to do is draw this little surface that they have. This A, and then what's below it, we'll go ahead and make this a boundary of a control volume. Okay, so let's go ahead and put a control volume below this AA surface. And so what we're going to have then is a force on the control volume we can say is caused, the only force on the control volume enacted by some solid boundary is here at the wall, which is the shear stress. So some of the forces could be viewed as shear stress at the wall times dA. Stress at the wall, dA is equal to, we'll say, all right, this is steady flow, so we don't want to include the ddt term, but we will have something that looks like m dot out u minus m dot in u, right? So this is just our momentum balance. Now, in general, we're going to say at this instant in time, we probably have, since the flow down here is the same as the flow up here, what's going in this side here is, in general, since this is fully developed flow, right? We've said that fully developed flow means it's no longer developing in space. Then what's going in this boundary is the same as what's coming out of this boundary, right? So the momentum flux through these two boundaries are equal. There's no momentum flux through there isn't really a boundary here to look at. We only have three, and then this boundary here is the only one that we're left with. In laminar flow, even, I've mentioned that laminar flow involves this nice sliding of sheets of fluid past one another with almost no mixing. That's true on a large scale, but with any fluid you have these random little molecular motions bouncing around, right? And so these molecular level, this molecular level randomness means that some fluid particles are going to travel in and others are going to travel out. And in general, the flux of mass in has to equal the flux of mass out, right? Conservation of mass in this control volume. So you're going to have some mass flow rate in equal to the mass flow rate out. M dot in equals m dot out. But in which of these two bodies is the velocity going to be greater? The one on top, right? We're showing from this velocity profile that any fluid that gets carried from here into here has a higher velocity than the fluid which gets displaced from here into here. So on a molecular level, where you have this diffusion or this transport of higher momentum into here, so this term is going to be larger, right, than, let's say, out basically U in is greater than U out. So this quantity here is going to be negative, meaning that tau wall dA is equal to is going to be negative or pulling in this direction, which is exactly what we see flows, right? Friction pulls against the flow velocity, and so the mechanism for creating this viscosity, this viscous resistance, is the sort of the molecular diffusion of momentum across this boundary. And so using this conservation of momentum argument, we can understand that it's the carrying of higher velocities across this boundary, and which are required to be slowed down by the fluid in this boundary that create this resistance to flow. Okay, word salad. But so that's the case with laminar flow. Turbulent flow, we could use the same sort of controlled volume analysis, but because turbulent flow involves these much larger scale random fluctuations, and what I showed in that video, right, turbulent flow involves really large scale mixing. The fusion is much greater in turbulent flow than in laminar flow. That means that things like temperature or salinity or a dye concentration, those get diffused, but so do vector quantities like momentum. So in other words, the high velocities here get spread out, and a greater portion of that momentum gets diffused across this boundary and into this control volume. So it essentially enhances both the M out and the M in terms when the velocity, when the flow becomes turbulent, and as a result, you get this. If there's greater diffusion, you get a larger shear stress in turbulent flows. So instead of this relationship, right, tau, this one that doesn't work, what we usually write is that the shear stress is equal to the this component, this background component, plus or minus this component here, rho times the average of u prime v prime. Okay, and in general, this quantity here is going to be negative, meaning that we can flip this sign here and write it as the laminar shear stress plus the turbulent shear stress. So we have these two components. One of them is caused by this good old Newtonian viscosity of the background flow, and the other is caused by this diffusion of momentum throughout the flow created by this enhanced mixing. So kind of as a demonstration, consider if we have like this boundary here in a laminar flow. Oops, that's not a very good video, but that's what we got to work with. We can see this if we have like something like a low temperature and a high temperature in laminar flow. The only diffusion of this temperature occurs on a molecular scale, creating this very slow mixing, whereas in turbulent motion, because of these random velocity fluctuations, it causes things to spread out much more quickly. And the same is true of velocities and momentum. This is a good demo of just how much mixing is enhanced in turbulent flow versus laminar flow. So what we've got over here is a very thick viscous fluid, low Reynolds number, laminar flow. And over here we've got tea and milk, both low viscosity, therefore high Reynolds numbers. What we can see is that just by inspection, we can look at this, we see all this random sort of clouding and mixing, which indicates that there's this random fluctuation. Whereas over here, as we mix, we get these sort of striations and this continuation of lines in the thick viscous fluid, which indicate that our diffusion here is not occurring very quickly. So this is just to demonstrate that the reason shear stresses are higher in turbulent flow is because those fluctuating components transport momentum from the higher velocity regions into the lower velocity regions more quickly. All right, so we've got this relationship for shear stress as a sum of laminar and turbulent shear stress components, and the idea is to see how we can actually get to this, if we can figure out what this shear stress, turbulent shear stress comes from. So let's suppose that we're not really interested in the random fluctuations themselves, right? If we're considering something like flow through a pipe, or flow over an airplane wing, or flow around a submarine, that all may be turbulent flows, we're usually more interested in the time averaged character of the flow. We want to say like how much flow is going through the pipe, or how much lift is being generated on the wing, or what's the drag on the submarine, and you ignore all those tiny little fluctuations, which indicates that we're really interested in this U-bar component, right? So we might ask ourselves, okay, can we take our governing equations, right, continuity, Navier-Stokes, and if we time average those governing equations, are we going to get governing equations that are just in terms of U-bar? The answer up front is no, but we need to explore why this happens, and in doing so, we're going to develop what are called the Reynolds averaged Navier-Stokes equations. So these are nasty. We're going to make them nastier by adding some more terms. But I just want to kind of frame what we're doing now. Conservation of mass, conservation of linear momentum. We don't care about everything that's in the U term now, and we're hoping to average out all those little fluctuations and just get equations that govern sort of the gross time averaged or slowly varying character of the flow. So if we wanted to solve for the steady flow over an airplane wing and say how much lift is being generated, you know, on average, forget all those tiny little wiggles around the average. If we just want that average value, what equations do we solve to get that? So the first one, and we're going to go through this kind of quickly to save time, but all of these slides are up on Canvas, and I think that they should guide you through the process pretty well. So if we take continuity, the continuity equation, conservation of mass, right? We usually write it as just du dx plus dv dy plus dw dz is equal to 0. If we take the time average of this entire expression, okay, what we get, we can split this into the time average of each individual component. Then we can make this substitution here, right, the Reynolds decomposition in for u, v, and w. So in doing this, we're exercising two properties. One is that time averaging is a linear operation. It means if you take the average of A plus B, it's the same as the average of A plus the average of B. And then we've plugged in our Reynolds decomposition here. So we can now rearrange these terms, right? For example, if we just look at just this term here, we can write it now as using the same linear property. We can split the U bar and U prime up, so we end up with partial U bar and partial U prime, each with an independent average over them. We know that this term here is equal to 0 because the average of the fluctuating component is 0. And so this leaves us with just du dx. And so doing this for the v and the y, or w components as well, we get the time averaged continuity equation. This is what we were hoping for, right? It's the same equation we were working with before, but now it describes just the time averaged flow. But before we move on, we could say, all right, I know this, but what if I go back and I undo this this time average and I just look at the regular continuity equation, make the same substitutions? I can now write it out as the sum of a time averaged continuity and a fluctuating continuity, which, since this component here, you know what? Since this component here is equal to 0 by this definition, we can take this component and say it's equal to 0 as well. And so we've learned two things from this time averaging. One is that if we're only interested in the average flow, yes, continuity or conservation of mass, taking the average of the governing equation over time does give us something that governs only the time averaged flow. But if we are interested in the instantaneous flow, we now also have an additional equation. We picked up one more governing equation, which tells us that the fluctuating component at all times must also on its own satisfy conservation of mass. Next, we move from, so that was the easy one. That's conservation of mass. Now we want to look at the Navier-Stokes equations. So let me pull this back. So here's Navier-Stokes as we've been using it and been writing it. Except this is supposed to be a dy here. Yeah. Give me a moment. There we go. Alright. There's our regular Navier-Stokes. So now if we take each of these terms, right? If we take the average of this whole thing, then by linearity, we've seen that it basically means the sum of the time average of each individual term. So putting the bar over the top of each thing in this equation in turn, we can sort of see what's going to go into the full time averaged equation. So the average of du dt, we can write out by this expansion, just gives us d dt of the time average du. That's easy. Same with the pressure fluctuations, right? Pressure, like velocity, in turbulent flow is going to have this random component. We're going to get the time average, taking the time average of p gives us, or of its rate of change, gives us the rate of change of its average. Same with everything in these components. The d squared u dx squared, we can see here, basically just turns into, again, because the average of this fluctuating component goes to 0, it falls out and we are left with only the time averaged component. So if you're like me, when you took a course like this, at this point you're kind of like, yeah, alright, this is pointless and boring, and why are we going through just averaging terms and showing that the same thing happens to each one? It's because these three terms have one thing in common. It's du dt, dp dt, and d squared u dx squared. All of these are linear terms. So we have linear terms, meaning there's no multiplication of u times du dx or du dc. Linear terms, we have averaging, which is a linear operator, and we have differentiation, which is also a linear operator. So everything here is linear, meaning that because it's linear, that it doesn't really matter what order we do the operations in, and the averaging will always get rid of the fluctuating component. However, these three terms here in our convective acceleration are nonlinear, and this is where things are going to get a little bit hairy. If we take, for example, just this u du dx term, and we time average it, making the substitution of our Reynolds decomposition in for u in these two places, we get this expression where we have u bar plus u prime times another component involving u bar plus u prime. So now distributing this whole thing and expanding it out, we have two components here, two components here. We expect 4 different terms to result. We'll now have a term involving 2 u bars, a u bar and u prime and a u bar, and 2 u primes. Okay. Now, we yeah, that was supposed to show up before. There we go. So because we know that u bar, the average of u bar is basically itself, it's a constant, and u prime here is the fluctuating component, then any component any term that involves u prime times u bar, once we take the average of it, it's going to go to 0. The same way that taking the average of just u prime gives us 0. Right? If we multiplied this by u bar, u prime, and took the average of that, we would just get u bar out front here, and we would just end up with a 0 times u bar, right? It doesn't change the fact that it comes to 0. So we can cancel out these two middle terms, leaving us with just this term and this term, which have been rewritten to account for the fact that the average is itself again. So we end up with u bar du bar dx. That bar doesn't need to be above the x, but whatever. And then the average of u prime du prime dx. So similarly, doing the same thing for the v and w components in the convective acceleration, we can write them using the same sort of expansion, meaning that the time average of our whole convective acceleration term can be written as a sum of a time averaged part and a fluctuating part. So one more manipulation to be done to this. If we look at, if we use the product rule, we can see that, for example, if we were to take the partial derivative of u prime, we would write it out, we would expand it out into two terms by the product rule, which means that, this is supposed to, there we go, this is what I wanted, which means that if we just subtract one of these sides over, we can write u prime du prime dx as the difference between its two components. So then, plugging this expression in for each of these terms, we can now write the fluctuating components as these difference terms, which by another simplification and grouping them in, and grouping everything out, can be written as the product, or the sum of these partial derivatives of multiplied terms, of these nonlinear terms, and then the product of u prime by these linear terms here. The unsteady continuity equation, right, the fluctuating continuity equation before told us that this is equal to 0, so we can cancel that out, leaving us with only this term. So we've taken our entire time averaged convective acceleration and turned it into this component here. So finally, if we plug everything back into the Navier-Stokes equations, we get something that looks like this. One more small manipulation. If we take the right-hand side and we factor out a row and just kind of shift things around, there's nothing too complicated here. At this point, it's just algebra. We can write the right-hand side here as being equal to the pressure force, gravitational force, and then these, we can understand, remember before it was, the equations of motion basically came down to, we ended up with negative dp dx plus gx plus d dx tau y x plus d dy tau, oh sorry, it was tau xx, tau y x plus d dz tau zx. Right, this is how we wrote the surface forces, or the forces on a fluid element, the partial derivatives of the shear stress components. And so we can see this takes the same force, or the same form, meaning that the components inside of these parentheses are actually shear stress. And so we recognize these terms that have the Newtonian viscosity coefficient as being what we will call the laminar viscosity terms, or laminar shear stress, and these other ones here as being the turbulent shear stress components. So the reason for taking you through that whole messy several pages of derivations was to show that we kind of went into this with the knowledge a priori that the shear stress was represented by a laminar component plus a turbulent component. And what we're seeing here now is that the turbulent component, remember it's a tensor, so the ij component of the turbulent shear stress is equal to rho ui uj times average. So what this really means is that this indicates sort of what I was talking about before, that advective behavior, the average advection of momentum in the I direction by the velocity fluctuations in the j direction. So this describes the extra turbulent stress that occurs, or the extra apparent shear stress that occurs because of a diffusion of momentum throughout the flow. And so we've shown that this is how we describe the turbulent stress, but this is also given another name that's more common in fluid mechanics, and that is the name Reynolds stresses. So this all comes from the fact that we used the Reynolds decomposition, right? This right here, to represent the velocity. We plugged that into Navier-Stokes and took the time average of it and arrived at this, which is called the Reynolds averaged Navier-Stokes equation. This is in the x direction only. We would have similar ones in the y and z directions. And the only difference between the Navier-Stokes equations and the Reynolds averaged Navier-Stokes equations are, A, we have these bar terms, right? We're not talking about average flow components, but also we have, we've picked up these fluctuating terms here. So we have an additional Reynolds stress involved in the forces on a fluid element. So at this point, it's wise to kind of step back and say, all right, we've got this new set of equations which describe turbulent flows, or the average character, or the slowly varying mean of a turbulent flow. How many equations, how many unknowns, how well defined is the system of equations that I have? So by these Rand's equations now, we've added three new components, this u prime, this v prime, and this w prime. These are all unknown. At the same time, a few slides ago, we developed one new equation, which was the unsteady fluctuating continuity equation, right? The one that says that du prime dx plus dv prime dy plus dw prime dz is equal to 0. So we picked up one equation. As a result, we now have 7 unknowns and 5 equations. This is not a solvable system. So this is kind of opens up the big can of worms that most CFD scientists, computational people, bang their head against for years, which is how to develop what's known as a closure model. They propose equations that give us, they propose sort of theories that give us 2 more equations that allow us to make a solvable system out of the Navier-Stokes and continuity equations. All right. This is something you're undoubtedly going to hear more about in later years, but I just kind of wanted to glaze your eyes over one time. So, this isn't supposed to happen yet. Okay. So we've got this balance of laminar and turbulent shear stresses. I want to write this out real big so we can reference it. Tau is equal to tau laminar plus tau turbulent. Okay. By the way, those equations, that we went through in the previous slides, those aren't specific to pipe flow. Okay, those are just the general Brand's equations. Well, those are useful for describing turbulent motions and the equations of turbulent motion on all sorts of bodies, not just in pipes. So I want to be clear about that. The next thing is that, remember from the last lecture, we talked about the idea of fully developed flow in a pipe. We did something where we took we had this fully developed flow going through a pipe, and we took a kind of a slug of fluid here and did a free body diagram on this element of fluid to find the balance between pressure forces and shear stresses on the element, right? And what we determined was that what we found was that the shear stress in a fully developed flow is equal to 2 times the shear stress at the wall over d times the radial distance from the center line. That is, we found that the shear stress varies linearly from the center line to the wall. It has this behavior like this, right? So it's 0 at the center line, maximum at the wall. And I pointed out there, when we did this, that none of the assumptions to get from this free body diagram to here, we didn't make any assumptions about laminar or turbulent flow. So this is actually valid for turbulent flow as well as laminar. Which means that in a pipe, regardless of the type of shear stress, it's always going to vary linearly from the center line to the edge of the pipe. Meaning we've got this, this is going to vary linearly. Linear on R. But how much of this is made up of laminar versus turbulent components is going to change with the distance around from the center line to the edge of the pipe. So in this diagram, what we've got here is this line here indicates the center line of the pipe, right? This would be the wall of the pipe, and this is our total shear stress. Okay, this is this term here, which goes from 0 at the center line to the wall shear at the wall. Then the laminar shear stress component is indicated by this black dashed line, indicating that really near the wall we have what's called the laminar sublayer, where right at the wall the flow almost never gets turbulent, right? It basically has to contour to the wall. And so it has to be laminar right at the wall boundary. And as a result, right at the wall shear stress is made up almost entirely of this laminar shear stress component. As you get further away from the wall, you pick up more of these random fluctuations, and a greater proportion of the shear stress gets made up of this turbulent component. So a general rule of thumb is that in the laminar sublayer, in the viscous sublayer, where the flow is basically stuck to the wall, the laminar shear stress is going to be greater than the turbulent component by anywhere from 2 to 3 orders of magnitude. And then as you move out away from the wall into what's called the outer region, or outer layer, the turbulent shear stress is going to dominate by about 2 to 3 orders of magnitude. This viscous sublayer in general is very, very, very thin. I think the number I read was that for something like a 3-inch diameter pipe, okay, fairly small. The viscous sublayer is about 1/1000th of an inch thick. Okay, so we're talking about a really, really thin layer of liquid stuck to the wall. The velocity profile that gives us this sort of shear stress, remember, if we've got, right, the laminar shear stress component is some function of and this is a function of This has to remain linear, but as I said, when it becomes turbulent, a greater portion of that shear stress is made up of this turbulent component. So out here in the outer layer, that means that more of the shear stress comes from these random fluctuations and less comes from the slope of the velocity gradient. And so if we look at the typical velocity profile of a turbulent boundary layer, really near the wall in the viscous sublayer, where most of the shear stress is laminar, it's coming mostly from a large velocity gradient, meaning that near the wall we have this really high slope in the velocity. Further away from the wall, as we get more and more fluctuation, and less of the shear stress comes from this velocity gradient, and so our velocity gradient flattens out here. Our velocity profile becomes much less dependent upon the distance away from the wall. We're going to skip those. And finally, this is the last of the slides. There are ways that we've developed over the years, mostly using dimensional analysis and very, very, very careful experiments to describe what this velocity profile looks like. So generally what they do is they say, all right, near the wall we have mostly laminar flow. Let's do a dimensional analysis of the viscous sublayer and come up with something that describes the velocity profile there. And so in the viscous sublayer, dimensional analysis has shown that the velocity profile and the average follows this relationship here, where this star component is what we call the shear velocity. This is or the friction velocity, and this is really just a substitution made. It's not actually velocity. We just call it the friction velocity because this quantity here has the same dimensions as velocity, is length over time. So this is a dimensionless expression for the average velocity over this term here, this shear velocity, is equal to the distance from the wall times the shear velocity over viscosity. So in the viscous sublayer, this generally does very well. This dashed line here, or this black line here, generally does very well at describing the velocity profile. However, as the flow goes into the outer region, right out here, it begins to follow a turbulent velocity profile, and in the middle, this is what we call the buffer layer. We have to sort of just kind of we have to play a game of matching the two different velocity profiles together. So we have dimensional analysis for the viscous sublayer and dimensional analysis for the outer layer, and in the middle we kind of have a blend of the two. This sounds very inexact because it's not very exact. As I said, turbulence is not well understood. We really have no idea what makes it tick. So the best that we're able to do as scientists is sort of put the tools that we have at our disposal into play. So actually, I lied a little bit when I said that was the last slide. This is the last slide. So we have that weird expression involving shear velocity or friction velocity that comes from dimensional analysis in the viscous sublayer. And in the outer layer, the most common, I should mention, sorry. This is what we call the law of the wall, or the wall relationship. And that means this describes the velocity for almost any flow really, really close to a solid boundary in the viscous sublayer. And further away, we have what we call the power law, meaning that the average velocity divided by, for a pipe, in this case, the centerline velocity, right? If this is our velocity profile, the average velocity at some point relative to the centerline velocity is going to be some component or some power of the distance from the wall. Okay, and this power from experiments can be shown to be a function of the Reynolds number. In general, most of the Reynolds numbers we consider with pipe flow, many that we consider in small vessel flows or large model scale flows, the Reynolds number is going to be in the range of about 10 to the 7th, or 10 to the 6th to 10 to the 7th. And so the most common choice of n for this power usually is 7. We typically find that 7 is is the 1/7 power law is a very common approximation for turbulent velocity profiles. And so the real thing here is the takeaway from this talk of velocity profiles is that if we have a pipe and we have a fully developed velocity profile, a laminar velocity profile is going to be parabolic. We solved that last time exactly using the free body diagram of this wedge. And if it's, so this is laminar, and if it's turbulent, we're going to get something that looks much weirder. It's going to be have the sharp slope near the wall, and it's going to be much flatter near the center line. The stress in the turbulent case is going to be much higher. And if we zoom in, sort of on this region, what we would see is that we have this in the viscous sublayer, we have this area where the velocity profile follows this scaling law of the wall, and then as we get further away, we have this power law relationship. And in the middle, we have to sort of blend the two. So we kind of have some mix between the wall law and the power law. And this is kind of the best we're able to do at approximating the velocity profile in in a turbulent boundary layer. Okay, so that wraps up our discussion of pipe flow. I know it's kind of this one was kind of a whirlwind of equations, but we'll be covering some more of the turbulence or some of the velocity profiles and boundary layers on Friday and next week. And those are going to be the topics of our last chapter on external flows. So also, just a couple of things. I have planned. There's going to be one more fairly short homework assigned next week. Okay, it's going to be assigned Monday and due on the last day of class. It's going to cover probably 1 or 2 questions about pipe flow, just kind of make sure you can get this stuff, and then some of the stuff from Chapter 9. So that'll be assigned on Monday, as I said. What I'm going to put up later today is that short pre-lab for Monday's lab. I'll post the lab groups, so I'll remind you guys on Friday, but the idea is just come up with those 8 predictions of water jet thrust that are described in the lab manual, and then show up for the lab. And that's an easy easy way to get to sort of pad your homework grade. And then finally, the optional kind of extra credit homework assignment of correcting 2 missed problems on your exam. So in the last minute, I want to hand out the exams. You guys can I'll call out your names and you can just pick them up from me and head out the door. So I've got Quincy, Grant, you know what? Christina, Sam, here's